Hello guys, welcome again to another interesting episode on our lecture or tutorial. We are still looking at design of reinforced concrete, and today we'll be looking at doubly reinforced concrete angular section. In our previous video, if you have been watching us in our previous video, we looked at the singly reinforced. Mind you, we are still trying to derive some parameters and equations which will enable us to solve problems in designing reinforced concrete. I mean, designing your slabs, your beam, your columns, your foundation, and all the elements of a building structure. So now we are still on the basis of trying to derive the equations and the parameters, which will now enable us, to do what we're going to do. So today we are looking at a doubly reinforced rectangular section. Mind you, we are still using our code, European code, Euro code 2, the design of reinforced concrete structures. So now look at the diagram before us. So this diagram shows that the section is reinforced doubly. Thus, reinforcement have been provided in the tension zone and also in the compression zone. Look at our neutral axis, this dotted line. You can see our neutral axis separating the tension zone from the compression zone. Now, the AS we are seeing here is our usual area of steel in the tension zone. Now, the AS prime you are seeing in the compression zone is the area of the reinforcement provided in the compression zone. You can see it. Now, your D prime is the effective depth in the compression zone. While your normal D is the D here is the effective depth, the usual effective depth from the previous video. Now you can see the strain diagram. You can see the maximum strain of a concrete 0.0035. You can see the EST, the strain of the steel. You can see the stress block. Look at the maximum stress we have in the stress block 0.567 FCK for the concrete. You can see your X value is equal to 0.8x. Now there is something here in this very place. We have two forces because now in the compression zone the two things are now there. We have the steel and the concrete. Now this FCC is the usual force of concrete in the compression zone, while your FSC is the force of steel in the compression zone. So here is your Z, your lever arm, Z bar, like the balance of the Z remaining. Now let's start deriving. Now at equilibrium, at equilibrium, you have to sum all the forces on the horizontal direction. You can see your FST pointing to this side, your FCC and FSC pointing to this way direction. So meaning at equilibrium, your FXT should be equal to your FCC plus your FSC. Let's call this our equation 1. Our equation 1 for simplicity. Mind you, in what we said last time, that when the design moment is greater than the ultimate moment of resistance, you have to go and provide reinforcement in the compression zone. So now the FST, this is now the force. Now look at the FST here. Force is always stress times area. Your stress times area. So the stress of the steel is 0.87 FYK multiplied by the area of steel AS. That becomes the force of steel is equal to your FCC. Your FCC here, which is force times area, which is the stress times area, 0.567 FCK multiplied by the area, your B, the breadth here, that the area of this stress rectangular and this stress block in the compression zone, that's BS, breadth and X, BS, plus your FSC becomes the stress 0.87 FYK multiplied by AX prime. Normally we know from our previous video, if you have been following us, Your FYK means the characteristic strength of your steel. The characteristic strength of your steel, it is always being determined when you take your steel to the lab for testing. That's where you see the strength of steel. But mainly by standardization, we have a 460 Newton per millimeter square, per mm square. Then some countries, some places use 510 Newton per mm square. But in my country, due to some variations and to make up for some irregularities, we usually make use of 410 Newton per mm square to be relevant to meet up, because there are some unforeseen, some irregularities, maybe some impurities, some factors that have been factored into it. That's why we make use of 410 Newton per mm square. Now let's simplify further. And now I have that for here x. This x, now look at x. X is equal to 0.8 x, but x is limited to 0.45 d. So I can simply say that x is equal to 0.8 x into, sorry, 0.8 into 0.45 d. So s becomes, can punch, and you can punch it. You have that becomes 0.36 d. By the time you punch your calculator, you see you have this. Now, taking moment at the tip or the point of this very force of steel. Taking moment at this very point. So we're gonna take moment right now. We have that is equal to this one. This young man will travel like this. Will travel like this. So the distance you're gonna travel will be um will be okay. Let's simplify this first. How that zero, how that my FCC becomes 0.567 FCK into. Let's substitute this x here. This x, which is 0.36d into 0.36d. So FCC becomes equal to, on punching your calculator, you should be able to have that it should be equal to 0.204 FCK BD. Understand? So now, let's now take our moment, taking moment about taking moment about the force of steel. Force of steel on the tension zone. Meaning I'm taking moment at this very point. So how does my moment becomes equal to this FCC we travel the lever arm distance, z distance to come in, because moment is force times perpendicular distance. Force multiplied by perpendicular distance. So I have that my moment becomes 0.204 FCK BD z bar plus this one. This is FSC. Moment FSC is 0.87 FY prime. So it will now be plus. Let me continue from here. Plus 0.87 FYK AS prime multiplied by, that will be D minus D prime. D minus, because you're gonna travel this distance from here down. So from here to here is my D. So the total D minus the distance of the effective depth in the compression zone, we have give the remaining distance at where this force of steel in compression will travel. So I have this. So let me continue again from here. Let me continue again from here. How that my M is equal to 0.204 FCK dd z bar plus 0.87 fyk ax prime into d minus d prime. But here z bar is equal to d minus s over 2. So just like saying s is this. So after the whole thing, my z bar becomes equal to my z bar becomes equal to 0.82 d. So by the time I substitute this 0.82 d inside this very equation, I have my m becomes equal to 0.165 f secant dd squared plus 0.87 fyk ax prime into d minus d prime. I can continue from this side. I can continue from this side. I decide to make as prime the subject. So making as prime the subject, I will simply have that as prime making as prime the subject. I have my as prime becomes equal to m minus 0.165 fck bd squared all over 0.87 fyk into d minus d prime, like this. So this becomes the formula for to compute or to find the area of steel in compression. This becomes the first parameter we are deriving, because we are going to be making use of these parameters during our calculation and solvings. So this is the area of steel in the compression zone. AS prime becomes the moment m minus 0.165 fck dd squared all over 0.87 fyk into bracket d minus d prime. Now I know something. The time we are solving for our singly reinforced concrete section, we know that the area of steel, the area of steel there is the area of the area of steel there is equal to m all over 0.87 fyk z, right? And then also from look of things here, z here, this z bar here, because we're talking about the z bar equals to d minus d prime. If you look at this equation very well, d from here now, the effective depth minus the other depth of this round will give you the z bar from here to here. So I simply make it this way. So if I should now substitute, I have that my AS prime is equal to wait, okay, it's equal to minus 0.165 FCK ED squared over say 0.875 into Z bar, simply Z bar like this. I'll go on further to simplify. I'm wiping here. I'll go on further to simplify by saying that AS prime is equal to over 0.87 FYK Z bar minus 0.165 FC square AD square over 0.87 FYK Z bar. Yeah, this is what it means. Simplification. So now I can now substitute everything here as equal to the area of CS, because that's what it is. If you compare this to this, that's the same. That's it. So I will now have that. I will already be wiping the board because I have a small board there. Therefore, AS prime is equal to your AS minus 0.165 FCK which is squared over 0.87. So therefore, area of C AS becomes AS area of C in the tension zone becomes AS prime plus 0. Let me arrange it very well. Very well. Minus 0.165 LCK BD squared over 0.87 C bar plus AS prime. This becomes the expression for finding the area of steel in tension. Find the area of steel in tension. So this is where we are. So with this, you can compute the area of steel in tension and also the area of steel in your compression zone. So with this, we have be able to derive all the necessary equations and parameters we needed. So in our next video, we'll start looking at the maybe design of slabs and other things. Thank you. Please always like our channel. Come to our channel, share it and hit the notification button. Thank you.